So we are going to start reviewing the last chapter in your textbook regarding on basics of radiation. And what we are going to cover on basics of radiation from this chapter is fundamentals of thermal radiation. That is very important when we are evaluating heat transfer phenomena. The theoretical foundation of radiation, definitions, and many equations to evaluate thermal radiation, blackbody radiation, and some important radiative properties. Also, we are going to learn how to evaluate radiation heat transfer, especially in two surface enclosures. Also, we are going to evaluate the radiation effect on temperature measurements and emissivity and absorptivity of gases and gases mixtures. So those are the main topics we are going to cover with respect basics of radiation. That is chapter 11 in your textbook. So let's start with some definitions as always. So radiation, by definition, is the transport of thermal energy by electromagnetic waves. What makes radiation different from conduction and convection? Well, this kind of heat transfer differs from the other two mechanisms in the way that it does not require the presence of a material medium to take place, right? For example, in conduction, what we need for conduction to take place? A solid, right? In convection, we need a fluid, right? Here, we don't need the presence of a material medium to take place. The theoretical foundation of radiation was established long ago in 1864 by the physicist James Clerk Maxwell. And he postulated that accelerated charges or charging electric currents give rise to electric and magnetic fields, and that these rapidly moving fields are called electromagnetic waves of electromagnetic radiation. And they represent the energy emitted by matter as a result of the changes in the electronic configurations of atoms or molecules. And we employ, and this is something that you might already revise in other courses, the quantum theory. Okay, so we continue then. The quantum theory is useful to view electromagnetic radiation as the propagation of a collection of discrete packets of energy called photons or quanta, and it was proposed in 1900 by Max Planck. And in this view, as already mentioned, hitting these two first lines, each photon of frequency is considered to have an energy equals to hz divided by lambda, where h is the constant, the Planck's constant, right? And here you have the value in international system, 6.6 10 to the minus 34 joules per second. And you have this value in tables in the back of your book, times the speed of the light divided by the wavelength. And this V is the frequency. So despite we need to focus on, despite there are several types of radiation, in this course we are going to focus specifically on thermal radiation. That is the kind of radiation that corresponds to heat transfer phenomena. And although all electromagnetic waves have the same general features, waves of different wavelengths have different behavior, right? And we classified these waves by the wavelength, but the value of their wavelength in what we name the electromagnetic spectrum, right? And here you have more or less the ranges of wavelength, right, to classify these waves based on the values or the wavelengths. And the electromagnetic spectrum that is here provided in this line includes cosmic rays, electrical power waves, gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, thermal radiation, that is the one that we are going to study a lot in this last chapter of heat transfer, microwaves and radio waves. And here you have some examples. For for example, radio and TV waves that are produced by the excitation of some crystals or by the flow of alternating current through electric conductors, microwaves that are produced by special types of electron tubes such as crystals and magnetrons, X-rays that are produced by bombardment of metals with high energy electrons, and gamma rays that are produced by nuclear reactions, right? And if you see, thermal radiation is within this range, right? 10 to the minus 1 to 10 to the 2. That is the area in the electromagnetic spectrum where we are going to focus in this last chapter, the thermal radiation. And the thermal radiation is emitted as a result of energy transitions of molecules, atoms, and electrons of a substance. And we typically employ temperature, right, as a measure of the strength of these activities at the microscopic level. Is what we have been doing all the time in this course, right? Focusing in this driving force that is the delta T. The rate of thermal radiation emission increases with increasing temperature. So at very high temperature processes is when we might need to think about including the effect of thermal radiation. Let's look at another term, important term, that is light. And light is the visible portion of the electromagnetic spectrum between 0.40 and 0.75 microns. And we consider a light source a body that emits some radiation in the visible range. For example, the sun. So that's an important definition, right? Another definition that we already, and we need to review at this point, and we already reviewed long time ago when we check on basics of radiation, was a black body, right? We said that a black body is a perfect emitter and absorber of radiation, and that the radiation energy emitted by a black body per unit time per unit surface area was given by the Stefan Boltzmann law, right? That was the Stefan Boltzmann constant that you have the value here. If not, you have it in the back of your book tables. Time the temperature to the fourth. Very important, this temperature is always absolute temperature for radiation phenomena, right? And here we are calling this EV as the black body emissive power. Another important term that we need to review, and it's in your book. We are going to go through a plot that you have in your book. So if you want to start locating, is the spectral black body emissive power. So this spectral black body emissive power is the amount of radiation energy emitted by a black body at an absolute temperature T per unit time, per unit surface area, and per unit wavelength about the wavelength lambda. For example, when we use this information, when you are interested in the amount of radiation an incandescent light bulb emits in the visible wavelength spectrum compared to that to the total amount emitted. And we use the Planck's law that is given in this equation to determine the spectral black body emissive power. And if you see this equation, Planck's law is C1, that is this constant, divided by lambda, that is the wavelength, exponential of C2, another constant. Lambda is the wavelength of the radiation emitted, and T is the absolute temperature of the surface. And if you evaluate this plot that you have in your textbook, I don't remember which page it is, but you have this 710. 710, you have this variation of the spectral black body emissive power with wavelength. You can see that by evaluating this plot of the wavelength versus the spectral black body emissive power, that the emitted radiation is a continuous function of the wavelength, right? At any specified temperature, it increases with the wavelength, right? Increases with the wavelength. The wavelength is the x-axis, increases. It reaches a peak, right? And then decreases with increasing wavelength, right? That's a common feature of all these of all these trends. Also, that at any wavelength, the amount of emitted radiation increases with increasing temperature, right? Which is pointing out to the idea that when you have very high, or you are evaluating phenomena in heat transfer at very high temperature, it might be important to evaluate also this emitted radiation, right? You cannot just discard it. Also, you can see that as the temperature increases, right? Here are the temperatures, guys, 100, 300, 500, etc. The curves shift to the left, right? They are moving to the left as you increase the temperature. To the shorter wavelength region. Then a larger fraction of the radiation is emitted at shorter wavelengths and higher temperatures. Okay, so again, it's giving you a hint when you need to add this contribution. The radiation emitted by the sun, so here you have solar, right? That's the sun, which is considered to be a black body of around 5,800 K, reaches its peak in the visible region of the spectrum. What is important to look at all these, and we are going to go through solar constants and all that. Well, because we have a lot of processes, right, that require that we evaluate these solar constants. So let's go through a problem so we can see how to use all the previous equations, the Planck equation and the Stefan-Boltzmann equation, to evaluate a black ball or a black body. So consider that you have a 20 centimeter spherical ball, and it's here in these images, at 800 Kelvin, and is suspended in air. Assuming the ball closely approximates to a black body, determine first the total black body emissive power, then the total amount of radiation emitted by the ball in 5 minutes, and finally, the spectral black body emissive power at a wavelength of 3 microns with Planck equation, right? Assume the ball behaves as a black body. So if it is a black body, which will simplify the analysis, right? So in order to determine the total black body emissive power, we are going to use Stefan-Boltzmann law. That is nothing more than the Stefan constant, right, times the temperature in absolute units to the fourth. So this, you have it from the previous slides, or again, you can read it from tables. Times the temperature. The temperature is already given in absolute units, so we don't have to do anything, right? So the Stefan-Boltzmann constant times the temperature absolute to the 4 give us 23.2 kilowatts per meter square. That means that the ball emits 23.2 kilojoules of energy in the form of electromagnetic radiation per second per meter square of the surface area of the ball, right? Again, if the ball is behaving as a black body. If it is not behaving as a black body, it's a different story, right? Then the second question was, what is the total amount of radiation emitted from the entire ball in 5 minutes? So that is determined by multiplying the black body emissive power obtained above this value by the total surface area of the ball at the given time interval, okay? So what is the surface area of a sphere? Pi d squared, right? So we have the diameter of the ball that is 20 centimeters. We just need to change it to meters, right? Because we are working in meters, everything. So that gives us a surface area of our sphere of 0.1257 meters square. At what time? Because the problem says at 5 minutes, right? So again, I'm going to change those 5 minutes into seconds. And finally, we can get the total amount of radiation emitted by the entire ball, the entire surface area, right, in 5 minutes or 300 seconds. So we have the black body emissive power that we obtained here in the previous question, times the surface area, because we want to know the total amount of radiation emitted by the entire sphere, right? Times the 5 minutes where we want to know that total amount of radiation. And here, well, we are just changing watts into kilojoules, right? So that is Q radiation 876 kilojoules. That means that the ball loses 876 kilojoules of its internal energy in the form of electromagnetic waves to the surroundings in 5 minutes, which is enough energy to raise the temperature of 1 kilogram of water by 50 Celsius. Note that the surface temperature of the ball cannot remain constant at 800 Kelvin, unless there is an equal amount of energy flowed to the surface from the surroundings or from the interior regions of the ball through some mechanisms such as chemical or nuclear reactions. Okay, so it's not going to be maintained constant, right? Something that you need to realize. The last question, what is the spectral blackbody emissive power at the wavelength of 3 microns? So that we're going to determine from Planck's distribution law. And these C1 and C2 values are constants, okay? So we have them. So you don't worry about C1 or C2. They are constants. We want to know at 3 microns, so that's the value I'm putting here for the wavelength, right? And again, the value of the wavelength here and the temperature in absolute units that we already have it given in the problem. So that gives us an emissive power at a wavelength of 3 microns of 3848 watt meter square of micron, right? And then this would be a point if we want to do a plot, right, of the wavelength versus the emissive power. Is what the book is plotting there in the figures in page 710, but this will be only a point. We need to plot several wavelengths in order to get a plot for the spectral blackbody emissive power for this particular ball. Okay, so let's go through other important definitions with respect on radiation, and an important definition is the radiation intensity. And it's a quantity that describes the magnitude of radiation emitted or incident in a specified direction in a space and is denoted by I. But this is a directional quantity, guys, radiation intensity. So we need to specify direction in a space. So the direction of radiation passing through a point is best described in spherical coordinates in the terms of the zenith angle theta and the azimuth angle sigma, as shown in the figure, right? So we will not need to know two different angles to determine the radiation intensity. The radiation intensity for emitted radiation is defined as the rate at which radiation energy dq is emitted in the theta sigma direction per unit area normal to this direction and per unit solid angle about this direction. So this would be the equation used to calculate the radiation intensity, where the solid angle W, this one, is defined as the angle at the center and has units of sterradian. And as you saw in the intensity, the radiation intensity equations, we are talking about two different angles. And one of them is a plane angle and the other one is a solid angle. So we need to see the difference between those two. And in order to visualize easily the difference between those, we can look at the pizza versus the watermelon angle, okay? And we typically work with more pizza angles than watermelon angles. And the plane angle or the pizza angle is, for example, imagine you have a circle of unit radius and the length of an arc is equivalent in magnitude to the plane angle. It's substance. It's whatever we do all the time, right? Both are 2 pi for a complete circle of radius R1. The solid angle is denoted by this W and its unit is a sterradian. In analogy to the plane angle, we can say that the area of a surface on a sphere of unit radius is equivalent in magnitude to the solid angle, its substance, like you can see here. Both are 4 pi for a sphere of radius r equals 1. So just imagine this in simple terms, why the intensity helps or depends heavily on the angle. Well, just imagine like if you are standing on the sunlight or near a fire, right? If you change your position or your angle from the fire, you will, the radiation heat transfer that you will feel, it will be different, right? If you are far away or if you move from one angle or the other. That's why it becomes very important in radiation, all these positions. However, since we are going through very basics on radiation, typically all these positions and angles, we have tables that we can read from them to approximate. So you don't really need to calculate all these angles, or geometry. So otherwise, this would be very complex. Obviously, if you don't have given these values from tables, you will need to calculate from scratch, right? But again, this is an introductory heat transfer course, so we are not going to go through all that complexity, but it's important that you have in mind that all these directions, all these angles, all these geometries plays an important role in radiation heat transfer. Let's talk then about more radiative properties. And one of them is epsilon, the emissivity of a surface. And it's something we already use. Remember that whenever we don't have a black body, we introduce the emissivity. And the emissivity, we said that is a value that runs from 0 to 1. And for a black body, obviously, epsilon or emissivity equals 1. And we have tables in the book for these emissivities, right? And emissivity is the ratio of the radiation emitted by the surface at a given temperature to the radiation emitted by a black body at the same temperature. And, well, you have tables in your book, but here is a graph that shows you the typical ranges of emissivity for different metals. For example, metals generally have low emissivities, as low as 0.02 for polished surfaces. The emissivity of metals tends to increase with temperature, and oxidation of metals can cause significantly increases in emissivity of metals or pure metals. For example, you can see here, right? Metals are here on polished. Polished metals are in the lower range. And if you oxidize the metal surface, you increase the emissivity range, right? Heavily oxidized metals can have emissivities comparable to those of non-metals. And well, that is clear here when you compare oxidized metals versus ceramics, right? And non-metals such as ceramics and organic materials typically have high emissivities. So they are in the range of large emissivity values. Other terms that we need to review is irradiation, absorptivity, reflectivity, and transmissivity. So irradiation is the radiation flux incidented on a surface and is denoted by G. So when radiation strikes a surface, like you can see here in this simple image, part of it is absorbed, right? Part of it is reflected. And the remaining part, if any, is transmitted, right? So absorptivity, then alpha, is the fraction of irradiation absorbed by the surface, like you can see here in this drawing. Reflectivity is the fraction reflected by the surface, and transmissivity, the fraction transmitted. So the radiation energy incident on a surface is the sum of the absorbed, reflected, and transmitted, right? And we can have different types of reflection from a surface, and I'm sure it's already something that you evaluate in other courses, possibly. That is the specular reflection and the diffuse reflection. The specular reflection is the mirror-like reflection, right? Like you can see here in this image, where the angle of reflection equals the angle of incidence of radiation beam. Diffuse radiation is when the radiation is equally dispersed or reflected in all directions. Reflection from smooth and polished surfaces typically approximates more the specular reflection, whereas reflection from rough surfaces approximates more the diffuse reflection. Let's look now into Kirchoff's law, and it's something that is going to help us to calculate an important amount that is the emissivity of a black body. So in order to understand the Kirchhoff law, let's consider that you have a small body here depicted by this pink zone that has certain surface area AS, certain emissivity epsilon, certain absorptivity alpha, at a temperature containing a large isothermal enclosure at the same temperature as shown, right? So this temperature equals to this temperature. Let's consider that a large isothermal enclosure forms a black body cavity regardless of the radiative properties of the enclosure surface, and the body in the enclosure is too small to interfere with the black nature of the cavity. Then the radiation incident on any part of the surface of the small body, right, is equal to the radiation emitted by a black body at a certain temperature T, or the temperature T here defined. Finally, you need to consider that the small body is in thermal equilibrium with the big enclosure, and the net rate of heat transfer to the body is 0. Then the radiation emitted by the body should be equal to the radiation absorbed by it, and that's Kirchhoff's law. Okay, so radiation emitted by the body equal to the radiation absorbed by it. That is the total hemispherical emissivity of a surface at temperature T is equal to the total hemispherical absorptivity for radiation coming from a black body at the same temperature. This relationship was first developed in 1860 by Gustav Kirchhoff, and that's why it's called Kirchhoff's law. So this is Kirchhoff's law, and it's something that you need to have in mind. So radiation emitted by the body equals to the radiation absorbed by it. And we're going to go through a Kirchhoff's law in a problem later. Now, we need to talk a little bit about the radiation effect. The greenhouse effect, because it's a radiation, direct example of a radiation effect. And just to locate you or give you an example in real life, is when you leave your car under direct sunlight on a sunny day. You will realize that when you come back, the interior of the car is much warmer than the air outside. Why? So the main reason is because the spectral transmissivity curve of most commercial glasses in cars resembles an inverted U. That is the figure here. So you can observe from this figure that a glass thickness encounter in practice transmit over 90%, right, of the radiation in the visible range, and is practically opaque to radiation in the lower wavelength infrared regions of electromagnetic spectrum. Therefore, the glass has a transparent window in the range of 0.3 here, right, around 0.3 here, to 3 microns, in which over 90% of solar radiation is emitted. And the entire radiation emitted by surfaces at room temperatures fall in the infrared region. So then the glass allows the solar radiation to enter, but does not allow the infrared radiation from the interior surfaces to escape. This causes a rise in the interior temperature as a result of the energy built up in the car. And this hidden effect, that is the consequence of thermal radiation, right, or heat transfer by radiation, is due to the non-grade characteristic of the glass and is known as the greenhouse effect. And it's just only due to this curve or the spectral transmissivity of the curve in the glass. So as you can see at the end, this kind of spectral transmissivity curves result in a heat transfer by radiation problem, right? Why? Again, because the glass allows the solar radiation to enter due to the shape of the core, but does not allow infrared radiation from interior surfaces to escape, so the heat builds up there. And we can see this also in the Earth, right? The greenhouse effect is evident on Earth. And you might know that the surface of the Earth, which warms up during the day as a result of the absorption of solar energy, cools down at night by radiating its energy into deep space as infrared radiation. The combustion gases, and we are going to see an example of this later in this lecture, the combustion gases such as CO2 and water vapor in the atmosphere transmit the bulk of solar radiation but absorb the infrared radiation emitted by the surface of the Earth. Then there is a concern that the energy trapped on Earth will eventually cause global warming and drastic changes weather patterns. It's important that you recall that some of the heat is trapped by the greenhouse gases in the atmosphere, and that's why, or that keeps our Earth warm and cozy on around 59 on average. So they are needed, but they are not needed in huge amounts, right? Because if the greenhouse effect is too strong, Earth warmer and warmer and warmer. And this is what is happening now. Too much carbon dioxide and other greenhouses in the air are making the greenhouse effect stronger. I mean, it's needed, but not that hot, right? And the ocean also absorbs a lot of it, but not all of the excess of carbon dioxide in the air. And as you can see, well, this is bleached. This is a bleached coral on the ocean just to the excess of carbon dioxide in the air absorbed by ocean water. So we are going to work on some problems of emissivity and absorption of these greenhouses. That is important that you have in mind the main rationale there, like why we are evaluating this in radiation heat transfer. And an important value that we need to have in mind is the atmospheric and solar radiation, because this is implied in most of the environmental problems that are related to radiation heat transfer. And here, the radiation energy emitted or reflected by the constituents of the atmosphere form the atmospheric radiation. And the solar energy reaching the air atmospheres is called the total solar irradiance. And the total solar irradiance, that is the solar energy reaching the Earth atmospheres, has a value of 1373 watts meter square. This solar irradiance is called the solar constant and represents the rate at which solar energy is incident on a surface normal to the sun rays at the outer edge of the atmosphere when the Earth is at its mean distance from the sun. And you might think, why this is important for us? Well, because sometimes you might need to design greenhouses, right? They have several purposes, or if you are going to design solar cells, that becomes important. All these radiation terms become important on such environmental applications. So the solar energy incident on a surface on Earth is considered to consist of direct and diffuse parts. The part of solar radiation that reaches the Earth's surface without being scattered or absorbed by the atmosphere is called the direct solar radiation. The scattered radiation is assumed to reach the Earth's surface uniformly from all directions and is called the diffuse solar radiation. The total solar energy incident on the unit area of a horizontal surface on the ground is given by this equation. That implies the direct solar radiation and the diffuse solar radiation, where theta is the angle of incidence of direct solar radiation, that the angle that the sun's rays make with the normal of the surface. And again, this becomes important if you someday want to work on problems related to solar cells or greenhouses. The radiation emission from the atmosphere to the Earth's surface is expressed by this equation, where T sky depends on the atmospheric conditions. and it ranges from about 230 Kelvin for cold, clear sky conditions to about 285 Kelvin for warm, cloudy sky conditions. Note that the effective sky temperature does not deviate much from the room temperature. Thus, in the light of Kirchoff's law, we can take the absorptivity of the surface to be equal to its emissivity at the room temperature. So this is just Kirchoff's law, right? Emissivity equals absorptivity. Then the sky radiation absorbed by a surface can be expressed by this equation, right? Emissivity, Boltzmann's constant, times the temperature of the sky to the fourth, right? Absolute temperature. So we are just putting everything now in terms of atmospheric values, right? And the net rate of a radiation heat transfer to a surface exposed to solar and atmospheric radiation can be determined from an energy balance. So is the sum of energy absorbed minus the sum of energy emitted. And if we input the previous values in the previous slides, we will finish in having this final equation, where Ts is the surface temperature in Kelvin, epsilon is the emissivity at room temperature, and a positive result of Q net by radiation indicates a radiation heat gain by the surface, and a negative result indicates a heat loss. Okay. So let's practice a little bit about absorptivity and reflectivity on a greenhouse. So you can see how to apply all the previous terms on solar constant, etc. Let's start with this problem: selective absorber and reflective surfaces. Consider a surface that is exposed to solar radiation. At a given time, the direct and diffuse components of the solar radiation are GD 400 and GD, the diffuse component, 300. And the direct radiation makes a 20-degree angle with the normal of the surface. The surface temperature is observed to be 320 Kelvin at that time. Assuming an effective sky temperature of 260 Kelvin, determine the net rate of radiation heat transfer for these cases. And it says, see the figure. In the figure, we have plotted lambda versus the emissivity, right? So we are going to evaluate a gray absorber surface that behaves like this, a gray reflector surface that behaves like this, a selective absorber surface that behaves like this, and a selective reflector surface that behaves with this kind of shape. So in this problem, we have a surface that is exposed to solar and sky radiation. And the net rate of radiation heat transfer is to be determined for 4 different combinations of emissivities and solar absorptivities, right? So we need first to calculate the total solar energy incident on the surface, right? And we have that equation in the previous slides. So we have that the total solar incident surface energy equals the direct solar radiation times the cosine of theta, that is the direction incident that is given in the problem, plus the diffuse solar radiation, right? So direct times the angle plus the diffuse solar radiation. We have this value. We have the direct solar radiation given as 400 watt-meter square. We have the angle. It says the direct radiation bed makes a 20 degree angle with the normal of the surface. So this direct radiation makes a 20 angle with the normal of the surface, cosine 20. Plus, we have a diffuse term of 300. So that gives us a total solar energy incident on the surface of 676 watt-meter square. Then we need to calculate the net rate of radiation heat transfer for each of the 4 cases. And we have this equation, right? This equation, we got it from the energy balance in the previous slide. So we need to plot the absorptivity here, times the total solar energy and incident plus emissivity, Boltzmann constant, and delta T of the surface and the sky, right? So let's do that, guys, for all the cases. So for the first case, we have an absorptivity of 0.9 and an emissivity of 0.9, or a gray absorber surface. So if we plot values in our net rate of radiation heat transfer for this case, it's going to be absorptivity times the solar energy incident on the surface plus the emissivity of 0.9 times Boltzmann constant times the temperature of the surface. Sorry, is hot minus cold, is going to be a sky minus surface. So sky minus surface give us a Q net heat transfer by radiation, or net heat transfer by radiation of 307 watt meter square for a gray absorber surface, which absorptivity is 0.9 and emissivity is 0.9. Let's do now for the gray reflector surface. So we are going to repeat these 3 times, just changing the absorptivity and emissivity values. The same energy balance for calculating the net rate of radiation heat transfer. So again, absorptivity of 0.1, right? The value of the total solar energy incident on the surface, plus the emissivity times Boltzmann constant times the difference of temperature between the sky and the surface, absolute to the 4th, because we are dealing with radiation. We repeat the same kind of analysis for a selective absorber surface, which has an absorptivity of 0.9 and emissivity of 0.1. So we repeat it for that, and we repeat it for a selective reflector surface too. So again, we are just changing absorptivity and emissivity. And you will note that the surface of an ordinary grain material of high absorptivity gains heat at a rate of 307 watt meter squared. The amount of heat transfer gain increases to 575 when the surface is coated with a selective material that has the same absorptivity for solar radiation, but lower emissivity for infrared radiation, right? That is the case of the selective absorber surface, because we put a layer that gives us this selective absorption, right? So it's increasing, right? Because you are increasing the absorption, the absorptivity. Remember that we have 3 terms there, right? Absorptivity, reflectivity, and transmittance. By putting this coating, you are increasing or enhancing the absorptivity. So that's why you are increasing the heat transfer rate from 307 to 575, right? So is what is saying here. Also note that the surface of an ordinary grade material of high reflectivity still gains a heat rate of 34 watt meter square. And when the surface is coated with a selective material that has the same reflectivity for solar radiation but higher emissivity for infrared radiation, the surfaces loses, that's why we have a minus here, right? 234 watt meter square. Therefore, the temperature of the surface will decrease when a selective reflector surface is used, right? Because you are reflecting. Remember, again, we have the 3 phenomena: absorption, reflection, and transmittance, right? So if you are reflecting a lot, you expect that your surface is going to be cooled down, right? That if you are absorbing a lot. And how you change that? By adding coatings. That's something that you can do. And those coatings are going to change the nature of your surface, so you can move absorptivity and emissivity values the way you need it for that particular process, right? For example, in a solar cell, you don't want that the solar cell heats a lot, right? Because it can damage the materials of the solar cell. So maybe you need a coating like the last one, a selective reflector surface, right? that decreases the temperature because you will have your material of the solar cell exposed hours and days on top, right? So that's this problem helps you to see that those kind of three phenomena and how you can play with that phenomena depending on the process you are dealing with.